Hi, Assalamualaikum and a very good morning. So today we're going to do some tutorial discussion for chapter 7 and we're going to focus on the subtopic of 7.1 acid and bases. So in today's video, we're going to look into the tutorial question 1, 2, 3, 4, 5, 6, 8 and 9 respectively. So without any further ado, let us start. So for tutorial question 1, for each of the following reaction, we need to identify the conjugate acid-base pairs. So for question 1, we have the reaction between the ammonia as well as the H2PO4 minus, which is in equilibrium to form NH4 plus with the HPO4 minus. As what you can see here, the acid here gonna loses proton H plus in order to form its pair, which is HO4, HPO4 minus. So when it loses a proton, then we know that it is an acid. And according to the Bronsted-Lowry theory, the same species, when it loses a proton, it's going to form a conjugate base. Okay, and this losses of H plus here will be taken up by the base, in which the base will add up a proton, so plus H plus, in order to form NH4 plus. So the base here, because it received a proton, and the partner of the NH3 going to be known as the conjugate acid. So in order to answer this question, we can draw a table like this. So we have the conjugate pairs, acid and conjugate base with its partner, which is the conjugate acid. So for question A, we have for question B1 here, we have our acid to be H2PO4 minus, and its partner going to be HPO4 minus. For the base, it's going to be the ammonia, NH3, and then the conjugate acid going to be the NH4 plus. Similarly, we're going to do the same process for the second reaction here. So for the second reaction, we have the CH3 and H2. So the similar species here is to be shown to be something like this. So it's going to add up a proton. So when it add up as when it adding up a hydrogen, then it's going to be a base. So here going to be a base, and then the partner here going to become a conjugate acid. Meanwhile, the HClO going to loses H plus, and because it loses H plus, we know that it's going to be an acid, and then the partner here going to become a conjugate base. So we're going to put it here. So our acid going to be HClO, and then its pair, which is the conjugate base, going to be ClO minus. The base going to be CH3NH2, and then the conjugate acid going to be the partner of the same species, which is the CH3NH3 plus, because it add up with H plus here. Alright, so this is how we answer question tutorial 1. For tutorial question 2, we need to define pH. So pH is basically a negative logarithm, which is negative log, or for the concentration of H plus or the negative log of the H3O plus, which is the hydrozonium ion. So in order to write the definition, we're going to write it in terms of the long full sentences, in which the pH is the negative logarithm of for the concentration of the hydrogen ion or the hydrozonium ion. And it can be also be written as the pH equal to negative log H plus, which is the formula. So for question A2 here, we need to calculate the pH of a 0.025 molar of the sulfuric acid, which is the H2SO4. So for the sulfuric acid, we know that it is a strong acid. Okay, so when it is a strong acid, we're going to use the IF table. Okay, so which is the initial, and then it's going to dissociate completely in order to get to the final concentration of the H plus ion. So for the H2SO4, we can start with writing the reaction at equilibrium. So because it is a strong acid, so it's going to have a fully dissociation, which is the H2SO4 aqueous. It's going to produce 2H plus aqueous ion, as well as the SO4 minus aqueous ion. And we're going to write the if table, which is the initial as well as the final concentration, because it is a strong acid. So for the initial concentration of the H2SO4, it's going to become 0.025, and at the initial stage, we doesn't have any concentration of H plus as well as the SO4. But as time goes by, at the final stage, this will dissociate completely in order to produce 2 multiplied by 0.025. So at last, we're going to get 0.050 for the concentration of H plus, and for the SO4 2 minus, we're going to get the concentration going to be 0.025. And by knowing the concentration of H plus, we can calculate the pH, in which the pH is equal to the negative logarithm of H plus, and we're going to substitute the value of H plus that we have calculated here, which is 0.050, and lastly, we're going to get the pH to be 1.30. So we know that 1.30, because we know that our pH scale starts from 1 to value of 14, so it has a value of 1.30, which is a very, very strong acid. And this is consistent with the value of the H2SO4. And now for question A3, we need to calculate the mass of the NaOH needed to prepare 500 ml of a solution with a pH of 10.0. So our NaOH, we know that it is a base. So from the pH here, we can find the pOH first, and then we can find the concentration of the OH. So in order to do that, we know that the pH plus pOH is equal to 14, and we can find the pOH, in which the pOH is equal to 14 minus the pH of the solution, which is 10, then we're going to get the pOH to be 4. So by understanding the pOH, we can find the concentration of the OH ion. So we know that our pOH is equal to the negative logarithm of OH minus is equal to 4. So once we do the maths here, we're going to get the value of the concentration of the OH minus to be 1 times 10 to the power of negative 4 molar. And from here, we know that the concentration of the OH minus is basically equal to the number of mole divided by the volume. So the volume given in the question is the 500 ml. And then we need to convert that into liter. So we can get the value here to be 0.5. And then the concentration here is to be as obtained in the previous working. So we can find the number of mole first from this equation. So the number of mole of the NaOH that is needed to prepare is going to be 5 times 10 to the power of negative 5 mole. And from here, we can calculate the mass, because we know that mass is equal to mole multiplied by the molar mass of the NaOH. So we're going to multiply it with 40, because the molar mass of the Na is going to be 23, O going to be 16, hydrogen going to be plus 1. So 5 times 10 to the power of negative 5 multiplied by 40, we're going to get the mass to be 0.002 gram. And this is how we answer tutorial question 2. Now for tutorial question 3, we need to write an expression for the dissociation constant for the propanoic acid. So when we know that it have a Ka value, we know that it is a weak acid. Okay, so when we know that it is a weak acid, we need to include water in our equation. So we have our CH3, CH2, COOH aqueous plus H2O liquid, which is in equilibrium because it is a weak acid. It's going to produce a propanoate ion, which is COO minus, and then the H plus here going to be accepted by the water here to form the hydrozonium ion, which is the H3O plus aqueous. And in order to write the Ka, it basically equal to the concentration of the product, which is the propanoate ion, divided by the concentration of the reactant, which is the CH3, CH2, COOH aqueous. And for here, we also need to include the aqueous state, which is the H3O plus. Okay, and for the water, we can ignore that because pure liquid is not included in the equilibrium constant. Right? So lastly, we're going to get our Ka to be the CH3, CH2, COO minus, which is our product, and then our H3O plus divided by the concentration of the aqueous CH3, CH2, COOH. Okay, so here are the equilibrium constant for the Ka for the propanoic acid. Now, we need to calculate the pH for the 0.35 mole per liter, which is the same meaning as molarity, for the propanoic acid at 25 degrees Celsius. So the Ka is given to be 1.35 times 10 to the power of negative 5 mole per liter. Okay, and from here, since we need to find the pH, we know that we need to know the concentration of the H3O plus. So from here, as usual, we need to use the ice table because it is a weak acid. So we can write the equation first, and then we're going to use the ice table, which is the concentration at initial, the change in the concentration, and then the concentration at equilibrium. And at the initial stage, the concentration is 0.35. And for the liquid here, we can ignore that altogether because liquid is not included in the equilibrium constant for the acid. And then at the initial stage, the ions is not present, so it's going to be 0 and 0. And as time goes by, the concentration of the propanoic acid will be reduced by negative x because it is a reactant. Meanwhile, for the ions, going to increase by plus x as well as the plus x. And at equilibrium, we're going to get the concentration to be 0.35 minus x. For the propanoic ion, we're going to get x. And as for the H3O plus, we're going to get the x. And then from here, we need to find the value of x by comparing it with our Ka. Okay, so we're going to proceed with step number 2, which is we know that our Ka is basically equal to the CH3CH2COO minus with H3O plus divided by the CH3CH2COOH. So it's going to become x multiplied by x become x squared divided by the concentration of the propanoic acid at equilibrium, which is 0.35 minus x. And then our Ka value is to be 1.35 times 10 to the power of negative 5 mole per liter. Okay, and from here you can use the assumption because our Ka value here is very small, which is times 10 to the power of 10 minus 5. So we can know that 0.35 minus x is basically equal to 0.35. So we're going to put it again here. And then our Ka is to be written as here. And then we're going to multiply it to the right hand side so that we get our x squared going to be 4.725 times 10 to the power of negative 6. And then we can find our x value, which is 2.173 times 10 to the power of negative 3, in which it refers to the concentration of the H plus or the H3O plus. Okay. And from here, you can also use, if you don't want to use the assumption, you can also try to use the quadratic equation, and you can also get to the similar answer. Okay, if you don't want to do the assumption, you can do that as usual, and then you're going to get the similar answer, which is this value here. And then you can do your pH because you know that pH is equal to negative log H plus. So negative log H plus, here going to be 2.173 times 10 to the power of negative 3. So once you do the math, you're going to get the pH to be 2.66. So the pH for the propanoic acid is 2.66, which is the weak acid. So this is how we answer tutorial question 3. Now for the tutorial question 4, the pH of a 0.1 molar solution of the weak acid, Ha is 2.85. So we know that the Ha will have a concentration of 0.1 molar, and then the pH here going to be 2.85. We need to find the Ka for the acid of Ha here. Okay, and since we know that it is a weak acid, we can start with writing the equation at equilibrium for the H sheet for the acid that dissolve inside the water. So first thing first, the equation Ha aqueous dissolve in water, which is H2O, and it's going to produce the H3O plus aqueous as well as the A minus aqueous. So from here, you can do the ice table, which is the initial molar, the change in concentration, as well as the concentration at equilibrium. So at the initial stage, the concentration of Ha going to be 0.1. Meanwhile, for the H2O liquid, we can ignore that because it's gonna be ignored inside the Ka expression. And for the history of plus, at the initial stage, it's going to be 0 as similar to the ions of A minus. But as time goes by, the Ha going to be reduced by minus X, and the concentration of the H3O plus as well as the A minus ion will be increased by plus S and plus X respectively. For the concentration at equilibrium, we're going to get the concentration of Ha to be 0.1 minus X, the concentration of the H3O plus to be X, and the concentration of A minus to be X. And then from here, you can proceed to the next step, which is you need to find the value of X according to the pH given. So you know that pH is equal to 2.85. So you can know that it is equal to the negative log H plus, and H plus is going to be equal to 10 minus 2 to the power of negative 2.85. And then you're going to get the concentration of H plus, which is also equal to X, and it is equal to the H3O plus to be 1.43 times 10 to the power of negative 3 molar. And for the Ka expression, we know that we need to divide for the concentration of the product divided by the concentration of the reactant. So we need to find the concentration at equilibrium first. So since we know the value of X, we can find the concentration of equilibrium for each species here. So for the third step, we can get the concentration of at equilibrium, in which 0.1 minus 1.413 times 10 to the power of negative 3. So once we do that, we get the value of Ha at equilibrium to be 0.09859 molar. And then for H3O plus and A minus, it's going to be 1.413 times 10 to the power of negative 3. Similarly, to go to the A minus. And then we need to write our Ka value. So Ka is equal to the H3O plus, which is the concentration of the product, multiplied by the concentration of the another product, divided by the concentration of the reactant, which is the Ha. And for the H2O, as mentioned, we need to ignore because it exists as a pure liquid. So for the H3O plus, the value is going to be 1.413 times 10 to the power of negative 3, multiplied by the similar value, divided by 0.09859. And then lastly, we're going to get the value of Ka, which is 2.025 times 10 to the power of negative 5 molar. And the unit here going to be ignored in this chapter. Alright. And now for the tutorial question 4b, we need to calculate the percentage of ionization of 0.1 molar of the hydrocyanic acid, which is HCN solution. So the HCN solution is basically a weak acid, and it has a concentration of 0.10 molar. So first thing first, we need to write the concentration at equilibrium when it is reacting with a water. So the HCN aqueous will react with water in order to form the hydrozonium ion, which is the H3O plus aqueous, and Cn minus aqueous. So in order to calculate the percentage of ionization, we know that it is equal to alpha, equal to the percentage of the H3O plus that is dissociated, divided by the initial concentration, which is the coming from the HCN. Okay, and that is why we need to find the value of X here. And then for the HCN, which is at the initial stage, we have it to be 0.1 molar. Okay, and from here we can do the ice level, which is the concentration of at initial, change as well as at equilibrium. So at initial stage we have 0.1. For the pure water, we can ignore that. And then for the H3O plus and the Cn minus, we're going to get 0 and 0. And during the changes, the reactant going to reduce by minus X, the product going to increase by plus X and plus X, and at equilibrium, we're going to get 0.1 minus X, and for the other species, we have got X and X respectively at equilibrium. And from here, we need to find the value of X by finding it with our Ka here. So our Ka is basically the concentration of the product, which is the Cn minus, multiplied by the concentration of another product, which is H3O plus, divided by the concentration of the reactant. And this Ka value here is referred to 5 times 10 to the power of negative 10. And then we know that our Cn going to equal to X, our H3O plus is going to be equal to X, and then our HCN going to be equal going to be inserted to be 0.1 minus x. And here we can make an assumption because we know that our Ka is very small because it is 10 to the power of negative 10. Then we can assume that 0.10 minus x is equal to 0.1. Okay, and from here 0.1 we can multiply it with 5 times 10 to the power of negative 10. We're going to get our x squared to be 5 times 10 to the power of negative 11, and then we can square root the answer here, in which we're going to get x to be 7.07 times 10 to the power of negative 6 molar. So here are the percentage of the dissociation or the x value at the numerator part, which is our history of plus. Okay, and in order to find the percentage of ionization, it's basically alpha, which is the concentration dissociated, history of plus, divided by the concentration initial, which is 0.1. So we're going to plug in the value here, and since we need to find percentage, so we're going to multiply it by 100%. So once we do the maths here, we're going to get the percentage of ionization to be 7.1 times 10 to the power of negative 3%. So this is how we answer tutorial question 4b. So for tutorial question 5, we need to find the pH of 0.1 molar solution of the phenylamine, which is the C6H5NH2. So C6H5NH2 are given the Kb value. So we know that it is a weak base. Okay, so we need to find the pH. So what we can do here, we can write the equation for the C6H5NH2 inside the water first, which is C6H5NH2 aqueous dissolved in water in order to form C6H5NH3 plus aqueous, as well as the hydroxide ion aqueous, which refers to the base. So we need to do the ice table, which is the concentration initial, concentration change, as well as the concentration at equilibrium. At the initial stage, we have 0.1 molar. And for the pure liquid water, we can ignore that in our ice table. And at the initial stage, the ions is going to be 0 and 0 respectively. So as time goes by, it's going to be having a change of the reactant to be minus x, the change in the product to be plus x and plus x respectively. At equilibrium, the concentration of the C6H5NH2 going to be 0.1 minus x. For the C6H5NH3 plus aqueous ion going to be x, and similarly for the hydroxide ion. So from here, we can find the value of x by comparing it with our Kb. So for step number 2, we can write our Kb expression first, which is the concentration of the product divided by the concentration of our reactant. So H2O is ignored because it is a pure liquid. And our Kb here is given to be 4 times 10 to the power of negative 10. So these ions here will have a value of x as well as x, so it's going to become x squared. And for the C6H5NH2, which is the phenylamine, it's going to become 0.1 minus x. So from here, we can know that we can make an assumption because our Kb is times 10 to the power of negative 10. So 0.1 minus x is basically equal to 0.10. Okay, and 0.10, when it's multiplied by this one, we're going to get 4 times 10 to the power of negative 11. So from here, we can square root these values here. So we're going to get the value of x to be 6.32 times 10 to the power of negative 6 molar, in which this x here refer to the concentration of the hydroxide ion. Okay, and for the concentration of hydroxide ion, from here we can calculate our pOH. Okay, so our pOH here is basically equal to the negative logarithm of the hydroxide ion, and we can insert the value of the concentration of the hydroxide, which is 6.32 times 10 to the power of negative 6, and then with our pOH we're going to get 5.20. But the question asks for the pH, so we know that pH is basically the summation of pOH is equal to 14. Since we need to find pH, so 14 is deducted with our pOH, which is 5.2. So our pH here is gotten to be 8.8. 0. Okay, and this is how we answer tutorial question 5. And for tutorial question 6, the table shows the base ionization constant, which is Kb, for the several selected compounds. So we have phenylamine, N2H4, ammonia, and then we have NH2OH. And then it's going to have a Kb value here. So we need to arrange the compound in the order of the increasing strength of the base. Okay, so as what you can see here, the Kb value is different for each different bases. Okay, and the higher the value of Kb shows that the basicity gonna be higher. Why is that? This is because, let's say if I'm gonna do the equation for the ammonia, which is NH3, when it dissolves in water, it's gonna produce the NH4 plus aqueous ion with hydroxide ion. Okay, and if I were to write the Kb, I'm gonna get our ions, which is NH4 plus with OH minus divided by the concentration at the reactant, which is the NH3. Okay, so when the Kb is higher, we know that our hydroxide ion going to be higher as well because it's going to be dissociated more. So from here, we know that the value of the -5 is the highest, which is the most basic. Okay, and this is followed by the N2HO4, and third we have the NH2OH, which is -8, and the least basic here to be the phenylamine, which is C6H5NH2. So for the strength of the base, we're gonna do the NH3 gonna be a stronger base comparison to the N2HO4, stronger than NH2OH, and stronger than the phenylamine. Now for question A2, we need to give the structure for the conjugate acid for each compound and arrange them in the order of the increasing strength of the acid. Okay, so dia terbalik lah. Kita nak susun dia according to the acidity. Okay, and from here you can write the conjugate acid pair. Okay, so this one is the base. When it receives a proton, it's going to become C6H5 NH3 plus. And then we're going to have N2H5 plus. And then we're going to have our NH4 plus. And then we're going to have our NH3 plus OH. Okay, and here are the conjugate acid. Since we are arranging in terms of the increasing acidity, so it's going to be the reverse of the order here. So because this one is the most basic, then this one going to be the least acidic. Okay, most basic, tetapi bila acid dia akan jadi least acidic. And for number 4 here, which is the least basic, it's going to become the most acidic. So number 2 going to become number 3, and then NH3OH going to become number 2. So the most acidic here going to become C6H5NH3 plus because it's structure of conjugate acid. And then the second one going to be NH3OH, and then we have N2H5 plus as well as the NH4 plus. And here is the most acidic. And here is the most basic. Okay, and this is how we do tutorial question 6 step by step. So for tutorial question 8, we need to calculate the pH of a solution containing 0.20 molar CH3COOH, which is an ethanoic acid, and 0.3 molar of CH3COONA. So this one is a sodium ethanoate. Okay, And basically here, it refers to the mixture of the weak acid, including with its conjugate base salt. So when there is a mixture of weak acid with the conjugate base salt, in which the ethanoic acid is consistent with its species, which is ethanoate, which is in the term of salt, we know that the combination of these two will form a buffer solution. So in order to find the pH, we can use the Henderson-Hasselbalch equation. So pH is equal to the pKa plus log CH3COONa, which is the conjugate base salt, divided by the weak acid. So pKa, remember, the weak acid going to be at the denominator part. So our pKa here is equal to the negative log Ka. So our Ka value is given to be 1.8 times 10 to the power of negative 5. The log for the concentration of the conjugate base salt, which is 0.3, divided by the concentration of the weak acid, which is the ethanoic acid, which is 0.2. So once we do the maths here, we're going to get the pH to be 4.9, which is the pH for the buffer solution. Now we need to calculate the pH of the 0.20 molar CH3COOH solution if there is no salt present. So when there is no salt present, we know that this part here is being eliminated. So when there is no salt, we know that it's not going to be a buffer. It's just going to be a weak acid. So in order to find the pH of the weak acid, first, we need to do the equation of the ethanoic acid inside the water. So we have the CH3COOH aqueous. So we're going to remove that here. And then we're going to produce CH3COO minus aqueous plus the H3O plus aqueous. So they're going to be an addition of H into H2O to form H3O plus. So as usual, we need to do the ice level, which is the change in the concentration as well as the concentration and equilibrium. So at initial stage, the concentration of the ethanoic acid going to be 0.2. The concentration of the water here can be eliminated because it refers to a pure liquid. Meanwhile, for the ions going to be 0 and 0 respectively. For the change in concentration, the reactant going to reduce by minus x. For the product of the ions going to increase by plus x and plus x respectively. So at equilibrium, we're going to get 0.2 minus x, x, and x. So in order to find the pH, we need to find the value of x first. So we're going to relate that with our Ka. So our Ka is H3O plus, which is the concentration of the product, multiplied by the concentration of another product, divided by the concentration of the reactant. The H2O going to be ignored because it is a pure liquid. And then our Ka is given as to be 1.8 times 10 to the power of negative 5. So it is basically x multiplied by x divided by 0.2 minus x. So x multiplied by x, we're going to get x squared. And then we need to apply the approximation because we know that our Ka value is very, very small because it has times 10 to the power of negative 5. So we can make an assumption in which 0.2 minus x is equal to 0.2. You can also use quadratic equation straight away and you will get the similar answer. So I'm just going to use the approximation here. So you're going to be x squared divided by 0.2 and then you're going to get the value here. So multiply by that, x squared is equal to 1.897 times 10 to the power of negative 3. And this x value here going to be used in order to calculate the pH. So the pH is basically negative log H plus, in which your x here refers to the concentration of the H3O plus, 1.897 times 10 to the power of negative 3. And then once you do the maths, you're going to get the pH to be 2.7. So the pH of the ethanoic acid, which is the weak acid, will be 2.7. So for tutorial question 9, we need to calculate the mass of the ammonium chloride, which is NH4Cl, needed to dissolve into the 30 ml of the 0.15 molar of the ammonia solution to form a buffer. And this buffer refers to a basic buffer. Okay, so we have our big base. So we have our weak base here, and then a certain amount of salt, which is a conjugate acid salt, and H4Cl going to be added into the solution of the weak base in order to form a basic buffer with a pH of 8.3. And then the Kb value here is given to be 1.8 times 10 to the power of negative 5. So from here, we can calculate the pOH first because we are talking about the basic buffer solution. So our pOH is basically 14 minus the pH, which is 8.3. So we have our pOH to be 5.7. And from here, you can use the Henderson-Hasselbalch equation in which the pOH is equal to pKb log plus log conjugate acid salt divided by the weak base. So Kb refers to the weak base at the denominator part. So our pOH is given to be 5.7. Our Kb value is given to be 1.8 times 10 to the power negative 5. And then NH4Cl is the concentration of the salt that we need to find out. And for the concentration of ammonia is given to be 0.15. So we can find the concentration of the ammonia, in which we're going to settle this part first, in which we're going to bring it to the left hand side. We're going to get it to be 0.9553. And then we're going to bring the log to the side here. So we're going to get 10 to the power of 0.9553 and then multiply by 0.15. And then you're going to get the concentration of the ammonia salt to be 1.353 molar. And from the concentration, you can find the number of mole because you know that the concentration is basically equal to the number of mole divided by volume. So the volume here is basically referred to the volume of the mixture, which is the 30 ml. So number of mole of the ammonium chloride divided by volume, in which the volume here is 30 ml, in which we have to convert that into liter, which is 0.03 liter. And the number of mole that we obtain for the salt is going to be 0.0406 mole. And from here, we can calculate the mass, in which the mass is equal to the number of mole multiplied by the molar mass. So the mass of the NH4Cl, so we're going to remove the bracket, is equal to mole, which is 0.040 mole. And the molar mass is going to be the molar mass of the ammonia, which is 14, hydrogen going to be 4, and then Cl going to be 35.5. So once we do the math, we're going to get the mass of the NH4Cl, which is the salt, to be 2.17 gram. So a certain amount of 2.17 gram of the ammonium chloride is added in order to produce a basic buffer. Alright, so I think that's all for today's video. See you again some other time. Bye!